Reduction reactions were discussed in chapter 18 when we were talking about aldehydes and ketones. We also talked about acidic chlorides and esters. And we said that those two are reduced by the strong reducing agent into a primary alcohol. Well, we're going to add to the list the acid and the acid anhydride. Both of these as well, they are going to be reduced into a primary alcohol by the strong reducing agent. So what we're doing over here is we are reducing the carbon of the carbonyl into a CH2. So the CH2 that you see in the product over here, this came from the carbon of the carbonyl. And then the oxygen of the carbonyl is going to turn into an OH, so your product is going to be a primary alcohol. During the reduction process, we will be losing the following leaving groups for each of the derivatives of the carboxylic acid. So we will end up having byproducts together with the primary alcohol. Sodium borohydride is a weaker reducing agent. So it doesn't work with any of the derivatives of carboxylic acids. It works only with aldehydes and ketones. We said that the mechanism of the reaction is way more complicated than this, but we're going to simplify the mechanism by representing the lithium aluminum hydride as an H-. The medium that we are starting with in the first step is a basic medium. Since I have just the lithium aluminum hydride, that's in the first step only. So the hydride is going to act as a strong nucleophile, and that nucleophile is going to attack the carbon of the carbonyl, form a negative charge on the oxygen. Because the medium is basic, the reaction is going to push the OCH3 to leave. The OCH3 now is a good leaving group because it is in a form of a lone pair and the medium is basic. You are going always to create the aldehyde as your intermediate. So in every single one of those, you are going to reach the aldehyde as your intermediate, but the reaction is going to proceed because we said that this one is a strong reducing agent. So it's going to keep reacting as long as you have a carbonyl in your solution. So now it's going to react again, attack the carbon of the carbonyl, form a negative charge, and then the oxygen gets protonated and you get your primary alcohol. As I mentioned, mechanism is way more complicated than this, but this is just a simplified version of the mechanism. So the base here, as a simplified version, the base is going to come, attack the carbon of the carbonyl, form a negative charge on the oxygen. The lone pairs are going to close. The OH is going to leave. In fact, over here, it's not the OH leaving because the OH is going to complex with the aluminum hydride. So it's that one that is going to leave. We know that OH is a bad leaving group. But for us to just take it as an OH leaving in this case to create the intermediate, which is the aldehyde. So once you form the aldehyde, the lithium aluminum hydride is going to attack again, form a negative charge on the oxygen, then it's going to get protonated, and still you're going to get a primary alcohol. Now, when you are doing the reduction, whatever is leaving is in a form of leaving a group that gets simply protonated. So if you're starting with a carboxylic acid, then your leaving group is going to be water. This one's going to be HCl. This one's going to be a carboxylic acid. And this one is going to be an alcohol. So what you're actually reducing is the carbonyl that is connected to the weak sigma bond. So in case of the anhydride, just one of the carbonyl is going to be reduced and the other one is going to leave in a form of a leaving group. Let's have an example here. This is a cyclic anhydride. So we're going to break the bond between the carbonyl and the oxygen. It is this carbonyl over here that is going to get reduced into a primary alcohol. The rest of the anhydride is going to pick a hydrogen from the second step and become an acid. Now, if you wish to isolate the aldehyde, then we are going to use a bulky reducing agents. These are hindered reducing agents. We've talked about two of those in chapter 18, the diisobutyl aluminum hydride and the tritertiary butoxy aluminum hydride. In each one of those, you are replacing the hydrogens around the aluminum except one with a bulky group. So in this case, you will limit the reactivity of the aluminum. Let's have an example here for the diisobutyl aluminum hydride. It's going to release a hydrogen that's going to attack the carbon, form a negative charge. Everything is going to close. The OCH3 is going to leave, and we're going to end up isolating the aldehyde. Reducing agent is not going to attack again because this is a bulky reducing agent, and here it is more hindered. So it's only going to attack once, and that's it, and you're going to end up getting your aldehyde. Please remember that sodium borohydride has no reaction with any of the derivatives of carboxylic acid. It only reduces the carbonyl of the aldehyde and the ketone. The ketone turns into a secondary alcohol. And if you have an aldehyde, it will turn into a primary alcohol. The lithium aluminum hydride will reduce both. Always the derivative of the carboxylic acid will always turn into a primary alcohol. And then depending on the carbonyl that you start with, so if you start with a ketone, then you're going to end up getting a secondary alcohol. If you start with an aldehyde, then you're going to end up getting a primary alcohol. The diisobutyl aluminum hydride will not react with any of the carbonyls of the aldehyde and ketone, but it will reduce the carbonyls of the derivatives of carboxylic acid and isolate the aldehyde only.